Welcome to EDU World Space.
For this problem on the topic of motion in two dimensions, we are given the coordinates as functions of time for a particle that is moving in the xy plane, where x of t is r into omega t minus sine omega t, and y of t is equal to r into 1 minus the cosine of omega t. We first want to sketch the trajectory of the particle, and we are told that this trajectory can be looked at as the point on the rim of a wheel that is rolling at constant speed on a horizontal surface. We then want to find the velocity components and the acceleration components of the particle at any time t. We want to then find the times at which the particle is momentarily at rest, the coordinates at these times, and the magnitude and direction of the acceleration at these times. Lastly, we want to know if the magnitude of the acceleration depends on time. So firstly, to sketch the motion of the trajectory of the particle, we know that the velocity or the x and y components positions are given. So sketching the motion or the trajectory of this particle on a tire looks as follows. So that's the xy trajectory of the particle. Now in part B, we want to find the velocity and acceleration components at any time t. Now we know that the velocity components will just be the first derivative of x and y with respect to time. So using the position functions above, we know Vx will be dx dt, which is r times omega, remember, which are both constants, into 1 minus the cosine of omega t. The y component of velocity Vy will be dy dt, and the time derivative of the y function is r omega sine omega t. Now, if we want the acceleration components, we take the first derivative of the velocity function with respect to time. So ax is dvx dt. And this is the same as the second derivative of the position, x d2x dt squared. So this gives us r omega squared sine of omega t, and the y component of acceleration is similarly dvy by dt. And this is r omega squared cosine omega t. So now we have our accelerations and our velocities for the particles, or for the particle at any time t. Next, for part C of the problem, we want to know the times at which the particle is momentarily at rest and the coordinates of the particle at these times. We also want to find the magnitude and direction of the acceleration at these times. So when the particle is at rest, we know Vx and Vy, the x and y components of the velocity, need to both be 0. And this is the case for every period. So this occurs at t is equal to 0, at t is equal to 2 pi over omega, 4 pi over omega, etc. Now at that time, we know that x is equal to 0, x is equal to 2 pi r, which is 1 revolution about the tire, 4 pi r, which is 2 revolutions, and so on. And y is equal to 0. Now the acceleration is a, and we know a is equal to r times omega squared in the positive y direction. For the next part of the problem, which is part D, we want to know if the magnitude of the acceleration depends on time, and to compare this to circular uniform motion. And the answer here for D is no. And this is since we can see that the acceleration A is equal to, if we resolve the x and y components, that's r omega squared sine omega t all squared plus r omega squared cosine omega t all squared all to the power half, which when simplified simply becomes r omega squared. So we can see the magnitude of the acceleration is the same as it is for uniform circular motion.